yesterday that I was going to discuss the benefits of multiple layers. So I am screen sharing. I hope that I'm screen sharing the right screen. I can't see. Try again. Let's do 2. So going deeper, you understand that the perceptron is a linear classifier by now. And you understand that it's a linear classifier because the output unit has a 0 or 1 function, for example, or value, but a 0 or 1 function that divides the part of the input space that is going to say 0 from the part of the output space that's going to say 1. So output space 0, output space 1. A line in the middle. The line we talked about yesterday in the context of Desmos. And if I'm sharing the entire screen, you have here one potential hyperplane. A couple of things to note here, where the intersects are in a network. So if you have here now a data set, and what is a data set? But a set of features for each individual in the data set. So if you have, say, 15 people, I guess that this notion is very already very intuitive to you, but allow me to belabor. You have 15 people and you measure 2 characteristics of them, characteristic A and characteristic B, so 2 properties, P1, P2, or activation 1, activation 2, as a function of input. You put activation 1 in the horizontal axis and the activation of 2, or the second property in the vertical axis. And you know one more thing, you know that this group of this data set, each of the members of the data set has a label, or has a set of labels really, but let's think about let's give them a label. Let's say the prickly people and the gooey people. So whatever it is like we're looking into, we're trying to separate prickly from gooey. And we want to do that via a very straight line. If there is a separation possible, you might imagine that the prickly people would be dots in this 2-dimensional plane, and you want to find the best separating line between them. So what I wanted to convey with this particular visualization is the idea that a 2-neuron input with 1 neuron output is producing 1 linear decision boundary. Very good. Now, what happens when you have more than 1 unit converging on a second unit? So these are the kinds of questions that I would like us to really ask as we're looking into these training procedures. For example, here, just to think about it simply before we go in, we have if I remove all hidden layers, the neural network that we have here has 2 input units, input unit X1 and input unit X2. What they're looking into are the features in this 2-dimensional plane of these data points. So you have blue data points and orange data points. Now, the first unit, and here's maybe I can ask you. So first unit is called X1, and it is producing outputs that vary from, say here the colors in the color bar, -1 to 1. So your input is wherever your data point is. So if your data point is here, and I'm drawing now, so it takes time for me to select. If your data point is this guy here, then it has a certain activation at the input and a certain activation at the output. So here we're looking into the input data set that we want to train as these myriad little dots. And they take values between 0 and smaller numbers, -6, -7. So our X unit is reporting on the horizontality feature of the data point. So it's basically saying that that particular member of the population, whether it's prickly and say blues are goose and or oranges are pricklies, we're saying that pricklies have little of whatever it is that the property in this axis is. So maybe it is snappiness, whatever, some property. So it's clear what the problem here is in the case of 2 dimensions, I presume. And so you have these two features here, x1 and x2. And with this type of data set, which is linearly separable, you can produce a strong separation boundary between the two. I'm using the ReLU activation functions. They actually don't have the heavy side activation function here. There are reasons for that, but there's not binary classification problems in this particular. But you can imagine that the ReLU function is 0 on one side, and on the other side is the value of the combination of the two. Remember how the ReLU function looks like? I'm going to go through the activation functions in a moment once again. In any case, what we want to then play with is our understanding of what are receptive fields of this network and what types of activation boundaries can these networks perform? Can these networks achieve? Because you're basically combining these hyperplanes of the pairs of neurons. So the idea that one input neuron and one or two input neurons and one output neuron are creating a boundary will be the case for no matter how many of these arrangements you have. So you're creating linear boundaries for whenever you have inputs and a single output in a single layer. So for example, here you see horizontal, vertical, but this neuron here, this hidden neuron, after training, and we're going to talk about training, it has already produced a boundary that gives us positive values on one side and 0 values on the other side, because it's blue and white. And that's because of the rectified linear activation. For example, we can also use hyperbolic tangent. We will get something that is similar, only like a bit softer. But let's start with something simple. So here you have these straight lines. Now, where do these straight lines come from? They're combinatoric in nature. But I want you to create precisely this type of intuition on the basis of the number of neurons. What is the complexity of the boundaries that you can produce? Working slowly, adding one neuron at a time, training, seeing what are the networks we can produce, seeing what is it that the hidden layer has acquired. Then you have like very funky data sets. They're really hard to classify. And so when I wrote here this document for the TensorFlow playground, the quiz, it is supposed to give us precisely the walking stones to discover a thing at a time about everything we're seeing. I'm definitely going to discuss these the general questions. I'm going to discuss them, but I also want you to, in the breakout rooms, discuss them once again to see if they actually got across. So the first step into the day-to-day after I tell you a little bit more about deep networks and slicing hyperplanes, is you will go through this with your group. If you have to rewatch the 3 blue 1 brown, you will go through this with your group after you watch it. These are very machine learning. So this is eminently a machine learning type of demo visualization. But it is I think, a very plausible metaphor for hierarchical processing. So we're basically selecting bits that the neuron is interested in, and these bits are areas in the input space. And we're going to try to chisel them, and depending on the output, what you want in your output, or the number of units you have in your output, you might select different types of features from this input space. And this gives rise to the metaphors of receptive fields. Here, when I hover the cursor over one of these intermediate neurons here, you're basically seeing the receptive field of that neuron. If that neuron would have been the output of the entire network, that is the decision boundary it has. Really, if you have more than one hidden layer, the decision boundaries in the second layer can actually be more complex. So here, for instance, don't know if you notice the top neuron and the bottom neuron no longer simply a linear boundary. They become combinations of those boundaries. More about that right now. So that's really the reason for going deeper, is because if you have only one single set of inputs and one single set of output, you can only produce linear boundaries. It's because you're not combining areas from the different neurons. So in the networks of, so this is a representation of a deep network. And if you have 3 layers of threshold units, we can generate arbitrarily complex decision boundaries. This is an incredibly strong statement. It's saying that no matter how funky your prickly and goo people are, if in your training data you have, they're sufficiently labeled, then you can't create a decision boundary to decide for them. But there's one thing that this slide here does not tell you, is that you might need a very large number of hidden units per layer to create these arbitrarily complex boundaries, because ultimately for every pair of neurons, you're creating a new line. So if you add a neuron, you're slicing the plane once again into sets of regions, the yes region and the no region. And they can be little islands, they can be non-convex, they can, overfit your data ultimately. So if you have like a perfect representation of prickly and goo people, but every single area is very close to the elements, you put, unseen versions of people will not be well classified, because the decision boundaries might not have been trained into that specific people. I'm going too fast here. What I want to say is that if you're creating a tessellation of space, that is, you're gridding it out with an arbitrary number of lines, you can always create one set of lines that perfectly categorize the data set. But this requires an enormous amount of neurons, and it's most likely overfitting. We're going to discuss a little bit of overfitting too. how do these decision boundaries come about? When you have threshold units, when you have the rectified linear function is a threshold unit. Or also like a non-linear unit. Let's talk about our activation functions here first. Anyone is unable to recognize any of these functions? So these are the sigmoid, the hyperbolic tangent, and the rectified linear function. So if I ask the crowd, what's the difference between the sigmoid and the hyperbolic tangent in terms of input space and output space? Can you tell me?
0 and 1 and -1, 1.
Yeah, okay. So just to make everybody aware of that. So they are, in dynamical systems, we will call them topologically conjugate because you can take a network of hyperbolic tangent neurons to be similar dynamically to a network of sigmoid units. So ultimately, there are reasons to select one from the other, but they are very much related to the problem at hand. I might have mentioned when in our sensory motor lecture that hyperbolic tangents are often used as output units for robots when we need an output that is the opposite of the other. Say, for example, you rotate a wheel forward or rotate a wheel backwards. You contract or extend the leg or contract. And the rectified linear unit, the important thing to notice is that it responds with a 0 to anything that is negative and a line, a linear function, with everything that is positive. If it had been completely linear here, like a line as a response, so this is often used for regression problems, you would not have the nonlinearity that is necessary to assemble hyperplanes. Now, let me give you an example of what I mean by assemble hyperplanes. So I'm making a drawing here. I don't know, maybe actually you can see. It's a bit deformed because of my camera. But here, what I have is a two-neuron network that is mapping onto another neuron. And I want my output neuron to be a heaviside function that divides the one side of the world from the other side of the world. It's basically an inequality. It's saying that the output of the unit 3 is this heaviside function of activation of unit 1 times activation of weight from 1 to 3 plus activation of unit 2 times weight 2, 3. So this operand here we saw yesterday is a line. And for different configurations of the weight matrices, you can have different lines. Now the heaviside function is dividing positive from negative. So basically you have a comparison. Is the operand here larger than 0 or smaller than 0? Now, because the operand can be, say, can be negative or positive, and the weights can create this line in different places. So you could have negative on top and positive on the bottom. So it really is arbitrary how you're dividing the space, if you're following me so far. Can you see this still? Is it too deformed? Now, if you have these two units mapping on a third unit, please, let's think about simple weights at first. Let's think about the weights as being simply like made of, say they're all unit weights to make the decision simple. If they're unit weights, then the decision boundary of the output unit is going to be a combination of these two spaces. And it's going to be a multiplicative combination because it's a threshold unit. So you gonna base it, the intuitive way to think about it is that you're reproducing the original boundaries. And then for each of the regions that are being formed, you're basically getting a sign that's the multiplication between the signs above. So for instance, here, the regions that will be positive are regions that were both negative and negative, or positive and positive. So for instance, this region here is positive here and here. And the region on the bottom is negative in both sides. So we are using a combination, like this is not that to create this the product of the two outputs. And similar here, then you will have the parts of the space that are negative. Now you can think about this analytically as well, because ultimately you can solve the following equation. And here we have, there's a shadow coming in, right? Where is it from? Oh. I hope that the shadow is not too disruptive. Is it all right? Okay, so ultimately, like I just mentioned, see the output of the year, you can compute, you can calculate for a network like this. Since now you have the adjacency matrix, you can calculate for a network like this, the output of this unit here, unit 5, as a function of everything that happened before. So let's start with these upstream units here. So the unit of the output of unit 3 is a Heaviside function. So I'm going to call it an F just to make it easy. So F of these activations plus the weight. So the activation of unit 1, W13, as we just had before, and 2, W23. But now, so the output of basically the output of unit 3 also includes sorry. The output now of unit 4 is similar. So you have the units 1 and 2 summing, but now you have different weights. And so because you have different weights and it can be positive or negative, you can have hyperplanes that are either separating negative and positive in one way or in another way. So this basically this would be 1, 4, and this would be 2, 4. And the activity at 5 is basically going to be a function of the sum of a weight multiplying. So let's say that this entire guy here is now output 3. It's a function of output 3 plus output 4. And you can see then that these guys continue to be here. So that's where these hyperplanes are coming from. We shouldn't forget that these functions are dividing space as a positive and a negative, and that these functions here are being multiplied. Sorry, I forgot something here in this. So F of W3503 times W35, which makes it multiplicative. 04 times 45. That's actually the output of unit 5. Because these lines are still represented here, but now they are basically scaled or shifted in different ways. You can, for example, flip the entire space. If you multiply this by a negative weight, for instance, if the weight here would be negative, it will flip the entire Heaviside function. So because if you had here now the Heaviside function, that choice of color. So here you have the Heaviside function and you multiply the inputs to the Heaviside function here. Say now is input X, okay? If I multiply X times -1, Now the Heaviside function for the function 1 minus x is flipped. I hope that you can see that. So if this would be the Heaviside function for x, this looks like the output of the Heaviside function for minus x. So if this weight then is negative, you're flipping the entire weight space. What I'm trying to say is that when these weights here in the original side are transferring, these weights here are transferring this space, they could also be multiplying by -1, and then this would be turned into a negative, and this would be turned into a positive in the product space. Okay, so so you know that these are the kinds of operations that we can conduct on the transfer functions. Allow me to go for a couple of slides more, and then I'll open for questions. Think if you have questions here, or basically also interrupt me if you want to. But else I'm going to just show you one more thing here. So I've been sharing the whole time, so you've been looking at, I hope that you'll be able to double click your little window and make it bigger, right? Okay, so here I continue with the share. So the operation on a space, when you're multiplying something by an input, say here I have a two-dimensional space, and I multiply one of the dimensions by 3. That means I have a scale of this grid. The grid is representing the distance between the points. Okay, so it's basically a metric grid. It doesn't have any. It's just representing every single point out there. Only that, you know, just as you would use ruler paper to draw something. Now you have this grid, and what you do is you multiply the x dimension by a certain value, you multiply a y dimension by a certain value. This will basically scale that grid. You can, this is the output of multiplying x minus 1. So if you're summing a bias to one of these dimensions, basically these dimensions being neurons, if you're summing a bias to one of these dimensions, you make it shift. Just adding a constant number. And so you're transforming the input space into the output space. The input space is the metric space formed by the grid. The output space is the result of the linear transformations of a single pair of units in the world out there, in the metric. So if, so let me then stop this for a moment and go back here to my page. So in the page, this was my input space, A1 and A2. But I tell you that the output space formed by, which is the output of neuron 3, is going to be a certain factor times unit 1, which we call the weight 1, 3, plus a certain factor times the second weight. So really, what output 3 is doing is picking up numbers that were in the original A1, A2 space. And one of the things that they are doing is they're multiplying by, here would be WA1, and here would be, say, because WA2, let's presume that W was a small number, and you get a new point that has been shifted here. If you had one input, given one input, it shifts over here. But it is doing this to the entire space, no matter where you are here, that operation is the same. You are multiplying the two components. This one is going a little bit down, and this one is going a little bit to the right because it's becoming bigger. So it goes here. So the entire vector field the entire transformation is very linear in that respect for this moment, and it's shifting them. if I now sum a bias to this point here, not only is going to go to the left and to the right by scaling, but it also going to shift by a bias. Now the multiplicative space is a little bit different. So this is the entire grid is going to shift. The multiplicative space arises from the fact that we are then adducing nonlinearity to this. Once you've scaled the input in one direction and then in the other direction, and then you added a bias that shifts the entire space a little bit further, or in one direction or another, you get this beauty where you saw the deformation here, which is basically the nonlinearity. Where is it? Here. So skewed by these scaling, shift, and squeeze. The squeeze operation is the nonlinearity. And here it is squeezing, but it could be a different kind of nonlinearity. It could be the heaviside function. If you had the heaviside function, it would suddenly paint two areas, one negative or 1, 0, and the other one positive, depending on the version of the heaviside you're taking. So 1, 0. Negating, bigger than. So I hope to have given you a sense of what the nonlinearity, so both the linear transformation on the hyperplanes and the nonlinear transformation. Did I succeed? More or less. Okay. Now, the need for nonlinearity. I will explain this in this slide. I'm going to read it out loud. I'm going to try to give you an intuition for it. But I think that you can get even more out of this if you go then to the playground to answer those questions and try things out. Try to think for yourself. What would it mean to this stuff that I've drawn down here if the functions would have been linear? So if instead of having a sigmoidal function, you just basically said, oh, well, let's ditch the function. Let's just say that the neural network can work via weights and activations, right? So what if it's a linear function? Try that, both in analysis if you feel comfortable, or in the playground to get a sense for why nonlinearity is required. The main intuition is the following. If you have adjacency matrices representing the entire linear transformation, okay, so you say you have first layer, it's an adjacency matrix because it's a feed-forward network. Second layer, adjacency matrix, feed-forward network. If you have a multi-layered network with only linear activation functions, you can multiply their matrices together and transform any number of matrices in one big matrix. Basically, it's to say that you can do the entire operation in one step. So even though you can have like 5 different intermediate layers, if the units, if there are no nonlinearities, next page. If there are nonlinearities, the combined product of, say, so this is a multi-layer network, and it has 3 units so that I don't have to draw a lot. So this set of connectivity here is going to be one matrix. This set of connectivity here is going to be another matrix, and this set of connectivity here is going to be another matrix. These 3 matrices, so the input here is basically transforming. This is a scale and a shift. This is a scale and a shift. and this is a scale and a shift. The composition, and this symbol is not plus, it's composition. The composition between these three matrices will ultimately result on some scaling and shift. If you now have a nonlinearity here, that means that parts of the output are basically excluded from the entire calculation or neglected, or some parts are less important or contribute less to the entire group. So you will have bits of network whose composition is not linear. So the moment that you apply a function here, you can no longer collapse them all together. So you can only collapse them together in the case that the activation functions of the individual neurons are linear. That's the fact. To do the proof is really a little bit like the slides that you see here. If you don't have the hidden layer activations, the function 1 of x simplifies to simply the sum of the sum of the sum. Right? So you collapse all of the weight matrices onto each other and you merge them together. So that's only possible if the activations are linear. But then you lose the ability of doing this, not that. A line cannot tell you this, not that. So a line cannot give you a category. Do you understand? So this should be very intuitively obvious. If I have a simply the transfer function, are you seeing things upside down? Do I have to draw upside down for you to see it correctly? Are you seeing upside down? No, right?
We see upside down, but yeah, it is kind of clear, like we can tell, I guess.
Yeah, right. Yeah, it didn't occur to me. Sorry. Maybe you should get a little bit of a little stand with a camera. That would be cool. Maybe in the future. If you have a linear transfer function, there is no natural place to say where something is big and where something is small, because ultimately, no matter where you go, there's no natural place to define a threshold. Whereas if you have a sigmoidal function, you would say, okay, well, over here, this is separating this from that. That's the need of nonlinearity. This separation here, this is more like a linear range, and this is nonlinear range. The nonlinear range is saying, okay, anything that is bigger than this is maximum. Anything that is smaller than this is minimum. And so it allows then for this compositionality of pluses and minuses to negate each other and to carve out what the output space should be like. And carving out the output space really does look like this when you have sigmoidal functions. I will want you to be carving out spaces from the playground in a moment from now. And just before I go further, the last thing I wanted to say is that we're talking. So this is very machine learning in tone, and so 4 terms have to be clarified from the outset so that we don't have to think about them anymore. But any machine learning problem falls into these 4 grand choices. So you choose a data set, say what you want to classify: pictures, people, behaviors, buyers, whatever. A model. What is a model? In machine learning, a model is specifically a type of architecture that does it. So a deep learning network is a model. But they think about this as, with tunable weights and with all of the parameters. So it's not like the kind of models that we sometimes use for computational neuroscience, in which you have a bunch of spiking neurons. In their case, the model is a model of the data. It's something that is able to categorize the data or to have the posterior distributions observing with high likelihood the input. This is the vocabulary that they often use. So the posterior probability, the likelihood. In any case, the model is a representation of the data set, is an optimal representation of the data set. If you give the same thing to the model as you give it to reality, you want reality to come out of the other end. That's basically the mindset of a model. A cost function can be many, but is some way of measuring the error. The choice of cost function often has to do with specific mathematical features of cost functions. So, for example, there are cross entropy category loss or minimization of the log likelihood. But I actually think that at this level we should really be thinking about the standard perceptron type learning error, which is simply target minus output. That if you did wrong, the sign of that was going to be negative, and you're going to have to go in one direction. If it is right, the sign is positive, and you don't have to do anything. That's and those things are in the 3 blue 1 brown videos. If you haven't watched them, go back to them just before we start. So it's almost 10 o'clock already, and this is then as much as I wanted to say. Just to remind you of what we're on about. So we're talking about having an error function. There are many kinds of error functions. Here I'll put them in the slides so that you can read about them later and just maybe find some links here and there. Some types of different category cross entropy loss, but I wanted to focus on the fact that most of the cases we are actually subtracting here the target of the unit minus the output of the unit, right? Times, so this is the weight going in, so because that's what you're going to be changing, and an eta, which is the error function. So this is at the basis of all of the learning of the loss functions. The reason why I'm focusing on this particular formula is that I want you to, this is the one that you might want to remember or have in your mind. So here in is the input of that particular unit K, and to the output unit L. So you have an input from, for every single input on the output unit L, you want to change their weights. And you want to change their weights in the opposite direction of the error. And this is then how you define gradient descent ultimately. It is the amount of error is defined by this equation, and then how you propagate it backwards through backpropagation is via the chain rule in calculus. And if I'm not forcing you to learn about the chain rule if you don't want to. I think that the explanation in 3 blue 1 brown is pretty good, and I can't hope to do a better job than this. But ultimately, you have a forward pass after which you compute the error, and then you propagate the proportional error as a function of how strong the weight was. So this is way too fast, and if you want to really go into this GIF, you might actually want to do one thing at a time, or maybe even look at backpropagation in 3 blue 1 brown once again, because he is going to give you computations of all the individual terms. But in any case, I mean, by now this is should be really straightforward. You have notice here that functions, that different neurons have different functions, F1, F2, F3, F4, F5, F6. Backpropagation works even if you have a network of mixed transfer functions. That's why these functions have little indices, is because they could be a different function per neuron. Let's not get bogged down by this. And so you saw here, this is basically the same thing that I was drawing before. So you have a function, and then you have the inputs that are scaled and multiplied. You go forward, these complexify, and you notice that here we still have he's working with the outputs of the 3 first units, no longer the outputs of the first 2 units. For every single layer, it is the same. It integrates ultimately the entire output of Y, but if the output of Y here, target being Z, and Y being the actual output, if Z is not Y, then let us change with a certain delta the weight between the output units and the unit that came just before. And that delta is the overall error that we just computed a moment ago. So the delta itself was here. And here, notice, we are just backpropagating as a function of weight for 6. So the responsibility of that particular connection is proportional to its contribution to the target that had a delta, that had an error. And then similarly here, when you're going further down the scales, backpropagation gives it gradient descent. Right, so the idea is that by using backpropagation, we're reducing the error. We're trying to reduce the error. Right? We take a pair of inputs, we backpropagate. That should have given us a little step down the error hill. So if here you have 2 parameters only, θ0 and θ1, thinking about, for example, 2 biases. This is an error function for 2 biases in the two middle units. You would like to, with a network with these 2 biases, you can change the biases in any direction you want, right? So in principle, you can arbitrarily select numbers for these biases. And if you select them arbitrarily, around you, you will find out that for certain selections, the error will grow. For other selections, the error will fall. This is how the surface was computed. Someone systematically selected all of the θ0s and θ1s for a learning problem and shown you what's this error surface like. But backpropagation should actually give you a reduction of error, since you're punishing the weight connections that are contributing to the error. So you're saying, okay, no, if you're contributing, then less of you. If you're contributing in this way by adding, I'm going to make you less. If you were contributing to the error by subtracting, I'm going to make you more. Right? So that's the entire idea. That's why then gradient descent works. And this is basically how you make a deep cake. You would initialize your weights with some random value. You run a batch of data through the network. Now know what a batch is via the Heavy Learning project. So a batch is a training set, like some things as you might have in a box. You then for each input you compute an error. You compare the prediction label to find the error value. You can sum over all of the output units. And then you apply some sort of gradient descent. Maybe you calculate the gradient of each weight using backpropagation. And you change each weight a step in the direction of its gradient. Now you see how the vocabulary becomes opaque quick. If you don't have a good understanding of what the gradient means, which is this local error function given a set of parameters, then this is already distancing you from understanding. But in any case, you're changing the weight a step in the direction of its gradient. It's correct. I mean, you're basically trying to go along the error gradient. And after using all of the training data, you can shuffle the data set and repeat. Then shuffle the data set and repeat will diminish the influence of sequence on the weights. So there is an influence of the data set presentation on the output, the general output. That's why often you call this stochastic gradient descent, is because the order in which you produce the data for training can be anything. So if you have a batch of 1 million pictures, you can present in one order, you're going to have one weight matrix. You present in another order, you're going to have another weight matrix. So you present it multiple times. Or maybe you cut your data set in two, and half of the data set is going to be your training data set, and the other half of the data set is going to be your test data set. You're going to see how well you've done, not using them to train it so that you're not incurring into problems such as overfitting. We're going to get there. But is this is what I had for the first hour today. I've overstayed my welcome. So it's 1 hour and 5 minutes now. Questions wherever they are, whatever they are. Was this clear? I don't believe it. Okay. So can you give me some thumbs up and some thumbs down just so that I can have a little idea of how you guys are going along here?
I think it kind of makes sense in combination with the videos. So like, I would like to like practice with it, and then I'll probably have questions. Like, you know, it's harder to like formulate
Perfect.
the
Yeah.
little things that
Exactly.
might not make sense yet.
That's precisely why I have like now the entire time of the rest of the lecture is basically breakout room time. So I'm just going to collect you at about 12 once again, so that we all go back together and share some insights about where we've gone. I should also let you know that in 10 minutes, our TAs are also going to be joining us. And so they're going to be helping me with to go into the different breakout rooms. And if there are no questions, I'm just going to create, yes, please, Chancellor.
Yeah, I was going to ask something, but maybe I can ask it during the break. I don't know.
You can also ask now. Let's see.
Yeah, like I watched videos and everything, and the things you told make sense, but I just didn't understand one thing. So after we do back propagation, so we change the weights. I didn't understand that process. Like after the back propagation, what do we do now? You know, like
you're done.
We change the weights, and then what do we do with those new weights? Like
so, this is your new trained network. So you keep those, and you keep those, and you might now present a different input, and then do that again.
And so that is a new network and with the new weights, and then we do.
Yes, exactly, because every weight has its own contributions to, or let's say every data point will make a different error.
Yeah.
Right. So say you have cats and dogs, and you present a cat, and that was categorized well. You do nothing with the weights. Now you present a dog, and it thinks it's a cat. Then you have to transfer. You have to change the weights, and you have to change the weights that are most responsible too, and then the back propagation will do those. And I think that's a very good question. It's an important question. So this is the idea of the batch. Mm-hmm. You present, and you can either do the back propagation step at every single data point, or you can do it at the end of a batch. If you compute the overall error, then you can also try to change the weights all at the same time. Depends on the problem, what you're going to use. In many problems, it's equivalent. But then the idea is that you would, for each you run batch of data. See, like in my slide, I had run batch of data through the network. So for each of the training works, like then you basically compute the error, then you accumulate all the error, then you backpropagate all the error, then you have a trained network. Presumably now, if you place you give the same batch data, you should have a smaller error, or at least some improvement. So basically, you can now test if your error has decreased after backpropagation, for example.
Yeah, and the slide that you showed, like about the cake, like supervised cake. So that is the new like training batch thing we do after the backpropagation. So to test it now with this one.
Yeah, so this is one potential order of things. So here it implies that you first run the data and compare the prediction of with label to find the entire error values. First, you do these two steps, and then you apply the gradient descent, right?
Yeah, so at the end of each batch. So
yeah,
it's a way of doing it.
Yeah, you can do it after a batch, and you can also definitely do it like element by element. In fact, yesterday I had downloaded a perceptron Wolfram demonstration to show you how it works in the individual when you're only training one single decision boundary. But since the playground here obviates it, I thought, you can do the same. So this is basically a perceptron. And then you can say, okay, perceptron, categorize this. So you have a bunch of things. I'm going to be discussing this in a moment. So thank you for the question. Let's, and I'll give you a little break, let's say a 10-minute break, and then I come back to explain the nooks and crannies of this playground here, and then we break out the rooms.
Could I ask a semi-unrelated question about the project from yesterday?
Yes, please. Tell me.
Let
me stop
like
recording for the
okay.
moment, just a second, so we have natural breaks.